Welcome back everyone. In today's video, I'll be explaining problem E from the AtCoder Beginner Contest 313. I'll provide the correct Python code in the video description, so please take a look after you've listened to my explanation. Let's start with the problem statement. We are given a string S consisting of digits from 1 to 9 with a size of n. We'll consider an operation denoted by a green arrow here and apply it to S repeatedly. This operation involves copying the integer si plus 1 times for each index I. Our goal is to determine the number of operations required until the length of S becomes 1. However, there are cases where the length doesn't decrease. Let's proceed with solving the problem. It's crucial to experiment with manual examples and predict potential answers for the problem. To begin, let's simulate examples with n equals 2. What insights can we gather from these examples? Here's the complete answer for n equals 2. Let S equals A and B. If A is not equal to 1 and B is not equal to 1, the operation continues infinitely. However, if A equals 1, we need B operations. Similarly, if B equals 1, only one operation is necessary. Next, we apply this idea to the case of n greater than 2. We treat S as a composite string of size 2 at a local level, and S is constructed from n-1 substrings. Therefore, for each adjacent pair of integers in S, at least one of them must be 1. Otherwise, the length of S will never converge to 1. This condition needs to be checked at the outset. From this, we deduce that our target string S contains many ones and only a few other numbers scattered within. This is where we introduce run-length encoding to simplify the handling of the string. We now have an ideal string configuration, but we are still not sure about the operation's behavior for longer strings. Let's conduct an experiment using the example S equals 31412. Verify that this example reaches completion after 17 operations. Through this exercise, you'll identify some important patterns. First, numbers within the string disappear from the end. Second, the count of 1 follows a certain rule and increases systematically. We should aim to track and record this count. Finally, the operation becomes simple when the last digits are 1. We aim to integrate these observations into our approach. Now explain the algorithm. Begin by defining a variable called count to keep track of the number of operations. Continuously remove the last integer a from S until the string is empty. If a is not equal to 1, a vanishes after a single operation, so we increment count by 1. Then we determine the index of the adjacent one. This index is calculated as the original index of 1 plus the number of operations multiplied by a-1. Consequently, we add count times a-1 to it. On the other hand, if the base number of a is 1, the term y1 to the nth vanishes after n operations. Here, we add n to count. Finally, when the algorithm concludes, the answer to the problem is count minus 1. This adjustment is necessary since the string operation terminates when the length is 1, but our algorithm continues until the length is not 0. This concludes the algorithm. Lastly, let's address a few additional points. Firstly, the overall time complexity of the algorithm is just n. This is due to the need to iterate through the string s both forward for run length encoding and backward to calculate the number of operations. Secondly, let's discuss why we don't terminate the algorithm when the length becomes 1. Consider another scenario where the string begins with some ones. In such a case, our algorithm would halt, leaving 1 to the nth, even though n-1 operations are still remaining. To avoid this ambiguity, we continue until the length is not 0. With that, I've completed the explanation. Should you have any questions about the problem or any requests for solving other ABC problems, please feel free to comment. Thank you for watching the video.